Okay, very good afternoon, students. So, just 1 minute, students. Okay, students. So, very good afternoon. So last time we started a new chapter. That's the solution thermodynamics. So we see first basics. Why we have to study the solution thermodynamics. In that, we said that system saving. Whenever the system saving gas mixture and liquid solution, at that time what happened, apart from temperature and pressure, concentration is also play a critical role. Concentration also a major role um, for the systems. So uh, so uh, in UG studies, we have only considering the change in systems within the only change in temperature and pressure. And in but here in solution, the concentration also changes. So concentration is changes due to the mixing and separation process. So if once you mix the two substance, the concentration is changes, concentration is decreases, while once we are doing the separation process, for example say we are doing the distillation. So once the number of moles of the transferring from one phase to another phase, so due to this reason there is a change in concentration compositions also. So in solution thermodynamics, we apart from temperature and pressure, we also have to study the composition or concentration. So to understand all this, there are certain properties come into the picture. A chemical potential, partial properties, fugacity, and excess properties. All these new properties are also come into the picture. So we also started to studying this theory, and we started one theory in solution thermodynamics, and that will be the fundamental property relations. In fundamental property relations, we know this four fundamental property relation in terms of internal energy, in terms of enthalpy, in terms of gas free energy. So apart from it, we take these relations. We can also derive for other relations, but gas free energy we can get many properties from the gas free energy. So we take dg is equal to vdp minus sdp. During that time, I will say that this one is for the 1 mole substance. This is for the 1 mole. So if you want to write down for the number of moles, at that time we can say dNg is equal to NVdP minus NSDT, where N represents the total number of moles. So if you want to study the functionality of two dependent variable, then we can consider df is equal to function of df or dx. If you want to if you want to understand the change in x with what is the change in f once we change in x with keeping constant y, so we have to use this mathematical relation. So what we have to see, we have to change in gas free energy once we change in pressure by keeping temperature and number of compounds concentration remains same, or there is a change in temperature with respect to change in gas free energy where pressure and number of concentration is same. This is related for closed systems. This is really valid for closed system. What happened? because in closed systems, so once we change in temperature and pressure, in closed system, number of the moles remain same, because in closed systems there is no mass in and out. The number of mass remains same. So we don't we add the extra term into concentration. So this is also valid for closed systems. Why? Because in closed system, number of moles remains same. And so once I compare with equation number 4 and equation number 2, I can find out the one relationship. Now, once you do the open systems, by open system there is a change in concentration also. In open systems, it's not like in closed system mass remains same, but there is nothing like in open system mass remains same. Apart from temperature and pressure, concentration is also changes, mass is also changes. In another words, there is a change in composition will be there. So for open systems, there is also a change in gas free energy with the change in the concentration. So let's say we have a ith species N1, N2, N2 up to ith species, and we write down this equation for open system. So apart from this first two, we also add the change in moles for change in gas free energy for N1, N2, and up to with that we can also write down for ith number of species. Now, the general equation for open system will be the change in gift energy is equal to dNg per dP with Na temperature and number of moles constant, where we do the whole summation dNg divided by dNi, T temperature, pressure, and apart from I species, all number of moles are same. So Nj meaning apart from the I species, all are the same things. Remember, multiply by d. So we see up to this, and now we go further from this. So this is the equation number 5. I would like to give this equation number 5. Then I would like to give this for equation number 6. Now let's go further. Right now I would like to define one new property that is for the solution thermodynamic, and the then new property will be the chemical potential. Chemical potential. The definition of chemical potential. Of species I in the mixture is we called as a mu I, and you also see this chemical potential. So like for example, what we say that if I am saying that it's a thermal equilibrium, so you said that the temperature is fixed. I am saying the pressure remain constant. So what is the mechanical equilibrium maybe we achieved? So the same way, for example, we are equilibrium in position, it means the chemical potential remains the same. You also heard this during the mass transfer. In mass transfer, we said that there is an equilibrium mass transfer condition here. So at that time, we said that the chemical potential remains same. So this is the chemical potential. We define chemical potential is equal to change in gas free energy with the number of moles for change in number of moles for I species at the time temperature, pressure, and apart from I, all moles are remain constant. So this is the chemical potential. So once I replaced dNg per dP with Nv with dng divided by dnd with minus n of s and mu I is equal to dng divided by dni pressure temperature nj. So finally we can write down the equation of nj. So d of nj, so d of ng is equal to dngp divided by dp is equal to, we write it down for nv, dng divided by dt, dou ng per dou t is equal to minus ns, and if we introduce mu I in above equation, in equation number 6, so equation number 6 we can write equation 6. So dng is equal to nvdp minus ns dt for summation of I mu I dni. Now if we multiply, this one is a 7, so I would like to write down this whole equation in terms of mass fractions, in terms of mole fractions, mass fractions. So what will I will divide by n this equation. So if I divide by n this equation, then I can say there is a d of g for of 1 mole, d of g is equal to vdp minus sdp per summation of mu I dni divided by n, where we can write down xi is equal to ni divided by n. So so equation number 8 we can write down. So equation number 9 we can write down d of g is equal to vdp minus sdt for summation of mu I multiplied by dxi, summation of mu I multiplied by xi, where this is the equation of 9. So this is the perfect the above equation described, or above equation is the fundament relationship. The above equation is the functional relationship between of molar Gibbs free energy to its composition, temperature, and pressure. Like this way, or we can also define using above one. We can also say that V is equal to dou of G or dou of P for temperature and X constant, where entropy S is equal to minus dou of G per dou of T per T multiplied by. So what nothing, just we see the relationship between the properties. Ultimately, if we see the relationship between the property, so now this is the one property relation with gives free energy. If you want to find out another property relation with enthalpy, then we can also define it. Let me write down the that for example, the enthalpy H is equal to G plus Ts. H is equal to G plus Ts. So we now we have a relationship between fundamental property gives free energy in here S. So S is equal to dou G per dou T with temperature and composition fixed. So I can put down S value here, and I can find out one new property relation. So G minus T multiplied by d of G per d of T d of X. What is the meaning of this equation? Gives free energy is expressed as a function of a variable, and it's also helpful to use to generating another functions, and which will use for the thermodynamic property relationship. So like for example, gives free energy is used to give a relationship between the enthalpy and another. So for example, if I take a system, if you want to find out the enthalpy, then we can use this one. Use this equation for with particular temperature and pressure and concentration, we can find it. So like this way, we can also find out another fundamental property relations. So this is the theory that fundamental property relation. Ultimately, goal is to be able to find out the relation between the properties using the closed systems and open systems. We can use this for, you can do it for open system, we can do it for the closed systems. Yeah? So we write like this way, we can also define it other property relation also. Yeah? And it will helpful to find out, it will helpful to understand the systems as a solution thermodynamics. Yeah? Now another theory that would like to understand, that will be the another theory with chemical potential and phase equilibrium. The next theory that would like to understand, that will be the chemical potential and phase equilibrium. Another theory that would like to understand the chemical potential and phase equilibrium. So ultimately, we understand if there is a phase in equilibrium, then what is the what is the chemical potential at that time. So I would like to take one closed system. In that they closed system, but internally they are open systems. So let me write down it. So we take closed systems closed systems in which there is no mass can enter in and out from a system. No mass can come from surrounding to system and no can go from system to surrounding. So system having two phase, system consisting two phase. So we have closed systems where we introduce a two phase. But internally both are open system because two phase are there. For example, liquid and vapor. Vapor molecules can go in a liquid. Liquid can also enter into the vapor phase. So number of moles of internally is changed. While internally two phase are contact with each other, but it means that internally they are open. Individual phase is open to other one, but both cannot change it within the surroundings. So the two closed system consists of two phase in equilibrium. Each individual phase is open to other and mass transfer between phases may occur. Then, so we said that there are two phases. One phase will be the alpha phase. There are two phases occur here. One will be the alpha phase and one will be the, I am saying, is the beta phase. So they are both are open to each other. Mass transfer will occur in between. So we can write down the equation for alpha phase. We can also write down the equation in terms of the beta phase also. So let me write down for alpha phase. So dng of alpha is equal to nv alpha dp minus ns alpha dt plus of ith component ui alpha dni alpha dngp of beta is equal to nv beta dp ns beta dt plus mu of 5 ui beta dni. Yeah? So for alpha phase and for beta phase, we can write down this equation. Now, here the equilibrium is applied due to the there is an uniformity of temperature and pressure. We can say the equilibrium exists. The equilibrium exists due to the temperature. Now, if we can write down like this one. For example, okay, there is dnm. I have a dnm, so I can say that nm alpha plus nm beta I can write down Nm is equal to Nm alpha plus Nm beta. So we take addition of equation number 1 and 2. So addition of equation 1 and 2, it gives a equation dng alpha plus uh, dng beta is equal to nv alpha dp plus nv beta dp plus minus, or I'm saying this one, if I take a sign, minus ns alpha dt plus ns beta dt plus summation of I u I alpha dni alpha plus summation of I ui beta dni beta. Yeah? Equation number 3. So we can write down according to the above equation, we can write down dng, its combined becomes 1, nv dt minus ns dt plus summation of I ui alpha dni alpha plus ui beta dni beta. Okay? So what I am saying that we can get this one. Now, if there is a closed system is there, if there is a closed system is there, then for closed systems, just 1 minute, I take this equation. If the systems are closed, then for closed systems, we say that we can write down this one for number of moles dng nvdp minus nsdt. The same way we have also here a closed systems where two phase are there. So using, if we have this two equation, then we for closed systems we can neglect this one for, because we have a fixed temperature and pressure is fixed. So finally we can cancel this one and we can say uh, 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 this is I mu I alpha, because there is a change in any systems is due to only the mass transfer will change. Otherwise, there is no change in temperature and pressure, so constant. So we can neglect it. So and we can say it's a summation of I mu I beta dni beta is equal to 0. Yeah. So here, once you study in the using mass transfer, we get one equation like if the one species are transferring from one to another, and another one will transfer from here. For example, okay, water and alcohol, we are separated with each other, but once the partition is removed, both are can interchange with each other. At that time, we say that DAB is equal to DBA, or one phase will be the positive, another we have to take negative directions. So due to this reason, we can say here dni alpha is equal to minus dni beta, because one mass transfer occur, one will be going in another side. So we can also say that dni beta is equal to minus dni alpha. If, why we are doing this? Because we have to take only one sign here. We have to write down only for one thing. So we can write down another one. It is summation mu I alpha minus mu I beta is equal to multiply by dni alpha is equal to 0 using this one. Now there is a change in number of moles of species I is independent. It is the change, the independent, and it's arbitrary. So quantity just 1 minute, students. बोलो okay, so quantities DNI is independent and arbitrary. So it's DNI. It's not depend upon anything. Then it's a number of moles. It's fixed. So so finally we can say UI alpha is equal to UI beta. It's a chemical potential of IH phase and chemical potential of beta phase. So only two phases are there. So both chemical potential are fixed in the sense that this phase is equilibrium. Here the phase is equilibrium. So what is the conditions of phase equilibrium in terms of chemically? So we can say that if chemical potential of both phases are same, then we can say is equilibrium conditions for the chemically. Or so if here is only two phases are there. If there is a more number of phases are there, then if pi phases are there, more than two phases are there, then we can say UI chemical potential for alpha, chemical potential of beta is fixed for the chemical potential of pi phase. It's a number of phases are there. Then they chemical potential are fixed. Then we can say it's a phase are in equilibrium conditions. So I am saying that thermal equilibrium, it means the temperature is fixed. I am saying that mechanical equilibrium, pressure is fixed. If I am saying the chemical equilibrium, it means the chemical potential remain the same for the phases. Yes, then so so this is the conclusion from this theory, chemical potential and phase. Ultimately, the multiple phases are at same temperature and pressure are in equilibrium when chemical potential of each species are in the same for all phases. Then and then we can say it's a equilibrium, phase equilibrium. So this is the theory of chemical potential and phase equilibrium. Now, next things we is partial properties. Next we have to see it's a partial property. So the three things I would like to say. Next theory will be the partial properties. There are three things. First will be the solution properties. M represent solution properties. So solution property, it means number of species are there, and combinedly we can say one property will be the solution property. We have to describe it as a M. For example, okay, solution properties are, for example, volume V, internal energy U, enthalpy H, entropy S, gives free energy G. So all are the solution properties. Now partial properties. So Mi bar, that we represent a partial property. So ith species property. So it's a ith species. There are a number of species in that we say there's a ith species properties. So we can say it's a partial property. So we can represent Mi bar. So for examples, Vi volume of ith species, Vi bar, sorry, Ui bar, Hi bar, Si bar, Ti bar. Pure species property. Another one will be the pure species property. For example, Mi is equal to pure species properties. ideally phase occur where the species are there. We can say it is a pure species properties. So we can say is a MI, for example. BI, UI, HI, SII, GI. So individual phases are occur in a pure species, pure state. At temperature and pressure, we identify as a pure species property. Again, a property of individual species which exist in a pure state at temperature and pressure, we consider as a pure species. Uh, uh, Now, next, whatever the theory are comes at that time, what ultimate goal will do the relationship between these one. Will do the relationship between all this one. It is the next goal for the chapter. So here we derive the partial property. We derive for the partial properties. How can we derive the partial property? Partial property we derive mi bar is equal to, there is a change in a solution property with respect to change in species, ice species, for the fixed pressure, temperature, and fixed other than the ith species. So partial molar property we can define dou n m divided by dou n I with fixed pressure, temperature, and other than I species. It's a partial molar property. It is a very good property and which will be helpful. In next class, we'll use this one for the next one. It means what I'm saying that the uh, there is a relationship between the two properties. For example, okay, next what our goal is to find out what is the relationship between it. For example, I am saying that mu I is equal to gi bar. So this one a relationship between the partial gives free energy, uh, partial molar gives free energy are same as chemical potential. I can say so. There is a relationship between the gives chemical potential as a solution property and give free energy as a partial molar give partial property. So there is a relationship between the solution property and partial molar property. So like this way we can define it. Uh, uh, we can define it. So now what we have to do, next time we'll see the theory, and that theory will be the derivation of Gibbs-Duhem equation, and ultimately from the next lecture we'll see the theory equation relating molar and partial molar property. So we'll define an equation. That equation it gives the relation between the molar and partial molar property. So once we know it, this one, then we can very easily deal within the thermodynamically what happening in solution. Then, so this is from my side. Then we go for the partial property, the binary mixture. Then we see the examples, and during after that we can also we also see the get examples. We also see it, and then we see the relationship among the partial properties. Then ideal gas mixture model. Then we go for the fugacity and fugacity coefficient. Likewise, we'll finish this theory. Okay. So now in solution thermodynamics, this is from my side. If anything from your side, then you can ask. If there is no question, then we can finish this meeting here. Thank you very much for attending it. Thank you very much for listening. I hope somewhat clear to you. It's somewhat difficult, but I tried maximum to understand you. So I think we end this lecture here. So tomorrow 12:30 to 1:30, I think we'll take by will be take by the JS sir. And right now he's not available, so I take it. But tomorrow from 12:30 to 1:30, the tutorial part will be taken by the JS sir. So right now I take his lecture. Okay, so we have a 9 to 10 lectures also there, and tomorrow we have only one lecture. Okay, so thank you very much for attending it. I end meeting here for